I am going to be talking about some rather speculative ideas this morning. Of course, this is a conference on quantum gravity, so that might be a redundant thing to say. So what do you do if you're in a field where there are interesting research programs, but certainly anything close to a complete theory, and certainly nothing close to a theory that is experimentally verified? Well, obviously, there are a lot of things that you can do, but one particular approach is to look for features that are shared by different approaches to quantum gravity in the hope that maybe they're saying something deep about what the theory really is, even if the details of the individual approaches turn out to be wrong. The classic example of this is black hole entropy, which is verified from enough different approaches that most, although not quite all of us, are reasonably convinced that this is telling us something fundamental about the quantum degrees of freedom of a black hole. Another less established example might be the existence of minimum lengths, which, again, is certainly not established, but in which there are intriguing hints from different areas of quantum gravity. So I'm going to talk about a third, which is much less well established. But over the past few years, there have been bits of evidence coming from a number of different approaches to quantum gravity that space-time, in some way that we don't really understand, behaves effectively two-dimensional at short distances. And there's evidence from lattice approaches, from renormalization group, from string theory, from the old-fashioned Wheeler-DeWitt equation, the number of other pieces of evidence that all point in this direction. So what I'd like to do this morning is to describe some of this evidence, propose a possible physical picture of what's going on, and then say a couple of words about directions that this might lead, although frankly, the answer is I don't know. But I can stretch that out for a slide. So, probably the strongest piece of evidence for this spontaneous dimensional reduction comes from causal dynamical triangulations. Now, Renato Lowell gave a very nice talk about this yesterday, so let me just briefly remind you that this is a lattice approach to the gravitational path integral, in which the integral is replaced by a sum over piecewise flat simplicial manifolds that have this extra feature of causal structure that prevents proliferation of baby universes and topology change. Now, at large scales, causal dynamical triangulations has some beautiful successes, which you heard about yesterday, including a phase that has the correct classical limit, that is, in which the ensemble average fits Euclidean de Sitter space extremely well, and which also has correct volume fluctuations in the sense that the volume fluctuations fit a mini superspace model that just involves the volume, but that comes naturally from general relativity. But what I'm interested in is the small scale structure. And here you run into the classical problem of quantum gravity, which is how to find observables or operators that make sense, that in this case, that, if you like, make sense in the entire ensemble of simplicial spacetimes that are being averaged over. and that probe something that is physically meaningful, even though they're looking at scales at which these things don't especially look like nice continuous four-dimensional spacetimes. The simplest thing you can ask about is dimension. And probably the best candidate for an observable that probes the dimension is the spectral dimension, or the dimension is seen by a random walker or a diffusion process. The basic idea of spectral dimension is very simple. It's that if you put a drop of ink in a d-dimensional container of water, the rate at which it diffuses goes down as the number of dimensions goes up, and the probability of a given molecule returning to its original point also goes down as the dimension goes up, simply because it has more directions that it can go. Quantitatively, diffusion is described by a heat equation, and for a manifold of dimension d, the short distance behavior of the heat equation is completely under control. There's a prefactor, there's an exponential that depends on the world function, basically the square of the geodesic distance, and then there are a set of corrections that involve higher powers of the diffusion time s. So the idea of spectral dimension is that if you look at this expression, or in particular if you look at the return probability, the heat kernel when x prime equals x, which gets rid of the exponent there, then you can read off the dimension just from the dependence of the prefactor on dimension. So then you can generalize this to an arbitrary system in which random walk or Brownian motion is defined without worrying about whether it's really a manifold. And then you define the spectral dimension as the thing you get from this exponent in a diffusion process. So as Renata Lohl and her collaborators first showed, and a number of people have checked and confirmed since then, if you look at causal dynamical triangulations, you find that if you're looking at large paths, that is, hold on, yeah. If you're looking at large paths, the spectral dimension approaches 4, or if you're doing a CDT analysis of a 3-manifold with 3-dimensional simplices, the spectral dimension approaches 3, which is a good thing. It means that it's one of the ingredients in a sensible classical limit. But that for both 3 and 4 dimensions, if you look at the spectral dimension at small scales, it goes down to, at least within numerical accuracy, to 2. This is I think, probably the strongest single piece of evidence for this short distance dimensional reduction. Now, as I said, there are a number of different observables that you could use to probe dimension in a situation like this, but spectral dimension is a particularly natural one for a physicist because the heat kernel is the Laplace transform of the Green's function, or the propagator. And so this behavior of the spectral dimension tells us that the propagator for a massless particle behaves as 1 over sigma for large sigma, which is what you expect in a 4-dimensional manifold, but behaves as log sigma for small sigma, which is the characteristic behavior of the propagator in a 2-dimensional conformal field theory. Second piece of evidence comes from the asymptotic safety program and the analysis of the renormalization group. We also have had a talk about this, so again, I'll just briefly remind you that the idea here is to start with the full effective action of general relativity, which has an infinite number of terms, so we don't know how to deal with it, truncate it to a finite but increasingly large number of terms, look at the renormalization group flow using the exact renormalization group methods, and search for non-Gaussian, that is non-free field ultraviolet fixed points, and hope that those are determined by a finite number of parameters, which then gives us something not quite the same as a renormalizable theory, but almost as good. Of course, the existence of such a UV fixed point is not proven, but there is a fair amount of evidence that such a thing exists. And so we can say, let's suppose that it exists and ask what the properties of the theory are near this fixed point. So in particular, it's a standard result in renormalization theory that operators acquire anomalous dimensions under renormalization group flow. And it's possible to show that that arbitrary fields that you put into such a model acquire anomalous dimensions at a UV fixed point such that their overall scaling dimension is that of the corresponding field in a two-dimensional field theory. You can look at propagators, and you find, again, that near the UV fixed point, there's this characteristic logarithmic behavior, which is, again, what you expect from a two-dimensional conformal field theory. There are ways of getting something like a spectral dimension, and that approaches to near the fixed point. There's a fairly general argument that I think is originally due to Procacci and Carini, that if gravity has a non-Gaussian UV fixed point, that necessarily propagators have this logarithmic behavior. And the overly simple hand-waving way of explaining this is simply that 2 dimensions is the number of dimensions in which the Einstein-Hilbert action is scale invariant. But there's an actual proof of this. OK, so a few other hints. The second oldest mention of dimensional reduction that I've found is from a 1988 paper by Addick and Witten, who look in string theory at the behavior of a high temperature, very high temperature gas of strings, and find that the free energy behaves as the energy of a two-dimensional conformal field theory. And in fact, they say explicitly in this paper that it really looks as if string theory at high enough temperatures looks like a lattice theory with a 1+1 dimensional field theory at each lattice site. I'll get to the oldest mention in a couple of slides. There is a suggestion from, by Modesto from loop quantum gravity, who, again, it's a simplified version of the argument, but he basically says, look at the area spectrum, take the factor of the Planck length and distribute it, that is, define a spin with length dimensions, that is, j times the Planck length. Then at large areas, the area scales with the square of this spin length, and at small areas it scales linearly, or approximately linearly, which again is the behavior you would expect from dimensional reduction. In causal set theory, the natural measure of dimension is something called the Myrheim-Meyer dimension. And Raphael Sorkin has pointed out that for a random causal set, this is a little bit above 2, perhaps just a coincidence. There's been some more recent work suggesting that in curved spacetimes, you need a slightly different estimator for the dimension of a causal set. It would be interesting to see what this looks like in that more sophisticated setting, but I don't know the answer. And then there are a series of other arguments. Crane and Smolin suggested quite a while back that if you have a gas of virtual Planck-sized black holes, that reduces the spectral dimension of space-time, although they didn't say to 2. There's work on multifractal geometry by Kalgani and collaborators. I'm told that a reduction to 2 dimensions appears in some sense naturally in non-commutative geometry, but I don't know enough about this subject to say anything more about that. I could also mention these anisotropic scaling models of Hojava, although there I think that the real lesson is that spectral dimension can reduce to 2 for a number of different physical reasons. In their case, it's because they're looking at a different diffusion operator and probably doesn't reflect a dimensional reduction. So that's just a cautionary note. So now let me get to the setting that led to the first, although widely ignored, idea of dimensional reduction. This is just the ordinary old-fashioned Wheeler-DeWitt equation, but in a short distance or strong coupling approximation. Usually people write the Wheeler-DeWitt equation in units where g is equal to 1, but if you keep g, or if you keep the Planck length, you find that the functional derivative term and the curvature term appear with opposite powers of the Planck length. So you can look at the strong coupling or short distance limit, the limit as LP goes to infinity. Now, of course, this is tricky because the Planck length is a dimensionful quantity, so it's not that obvious what it means to send it to infinity. But if you like, you can think of this as saying that we're looking at the behavior of the solutions of the Wheeler-DeWitt equation on scales that are small compared to the Planck length. So if you do this, what you notice is that the only term involving spatial derivatives drops out in that limit, and you get an ultralocal limit, a limit in which space-time points effectively, or spatial points effectively decouple from each other. Not quite, because there's also the diffeomorphism constraint, but very nearly. There was a lot of work on this in the 1980s and early 90s, and you can solve the Wheeler-DeWitt equation in this limit and do perturbative expansions around 1 over LP and get a lot of information. For my purpose, it's good enough to look at the classical behavior, or if you like, at coherent states. And there, the answer is that in this LP goes to infinity limit, you get disconnected points or disconnected small regions of space-time, each of which look just like Kasner space. When you put the Planck length back in as a perturbation, you get BKL behavior, which I'll say a little bit more about later. But essentially, each small region behaves like a mixed master universe, that is, a Kasner universe with random axes, but which occasionally bounces in a way that changes the axes and the relative expansion rates. So I'm claiming that this is a signal of dimensional reduction. So let me explain why. First of all, for those of you who haven't taken your GR course within the past 4 or 5 years and don't remember Kasner space, this is it, with an additional restriction on the exponents, P1, P2, and P3, namely that their sum is equal to 1 and the sum of the squares is equal to 1. These restrictions mean that 2 of the P's are going to be positive and 1 negative, which means that as t goes forward in time, you have 2 expanding directions and 1 contracting direction. Or as t goes towards 0, you have 2 contracting directions and 1 expanding direction. So you can take Kasner space, pick an arbitrary initial point, pick a geodesic going in an arbitrary direction, and look at what the proper distance, look at what part of the space that geodesic explores after some given time interval. What you find is that the proper distance along a random geodesic in Kasner space is almost entirely in one direction. So that, in effect, even though Kasner space is certainly a 3+1 dimensional manifold, in effect, a geodesic that travels at a reasonable distance only explores one dimension. Another symptom of this is that if you look at Kasner space towards t going to 0, you find that the particle horizons shrink to straight lines. So again, an indication that in some sense you're getting 1+1 dimensional behavior. Now this sort of thing ought to show up in the heat kernel and the spectral dimension. As far as I know, no one has managed to exactly calculate the heat kernel for Kasner space, but a number of people have done different approximations, and what they find consistently is that for small enough t, compared to the diffusion time, the heat kernel, the S term in the correction to the heat kernel dominates, so the heat kernel goes as 1 over S rather than 1 over S squared, which means the spectral dimension is 2. Now, this was first noticed by Hu and O'Connor in 1986, who talked about the idea of an effective infrared dimension and argued that for Kasner space that was 2. I would have said ultraviolet dimension, but that they meant what I mean. For BKL behavior, you have this same kind of Kasner space-like choice of a preferred one spatial dimension, but it's essentially a random and chaotically varying spatial dimension. So you have a sort of dimensional reduction to 1+1 dimensions, to effectively 1+1 dimensions, but with a random spatial dimension. Okay, so BKL behavior was not discovered in this context. It was discovered in cosmology as the likely generic behavior of a cosmology near a space-like singularity. And there's been a lot of work on this, and there's a fairly good understanding of why this happens. And the basic reason is exactly this decoupling of nearby points. In cosmology, this is called asymptotic silence, the idea being that point can't hear its nearby neighbors. It's also sometimes called the anti-Newtonian limit. It's the limit in which the effective speed of light, rather than going to infinity, goes to 0. The light cones shrink to time-like lines. Neighboring points decouple. Once you have that behavior, you automatically get BKL-like behavior with some possible exceptions. And therefore, you would get this kind of effective dimensional reduction that I've talked about. So the natural question is whether there is some way that this is a characteristic of space-time, not just near a space-like singularity, but generically at short distances, which is what this strong coupling limit of the Wheeler-DeWitt equation suggests. In loop quantum gravity, as we heard in Barrow's talk on Monday, it's been suggested, at least in some approaches to loop quantum cosmology, that this happens near the critical density. And you can ask whether this is a property of the density or a property of the length scale. Another way of getting at this, by the way, which is in progress, I'll mention briefly, is that you can go back to causal dynamical triangulations and try to analyze the shape of the light cones and see if at short distances they really do have this non-symmetric behavior. One of my students, Charles Pierce, is working on this. It has turned out to be technically much more difficult than we had hoped. So it may be a while before I have an answer to that. No, what you can do is take, CDT has a time foliation, so you can take a cross-section of a light cone at a given time. You can then take a measure of the ellipticity of that cross-section, and then that is a coordinate-independent characteristic, which then, in principle, you can average over the ensemble. Okay, so let me give you one beginning of a piece of evidence for this kind of behavior at short distances. So we're looking at the behavior of light cones, and these are governed by the Ray-Choudhury equation. If you look at the expansion, that is the logarithmic derivative of the area of a pencil of light, the derivative along the affine parameter, then that expansion solves a simple differential equation involving expansion, shear, vorticity, and, well, the Ricci tensor, and I've used the field equations to convert that to the stress-energy tensor. Now, let's suppose that we can find a regime in which a semi-classical analysis makes sense, that is, in which we can look at quantum fluctuations of the stress-energy tensor, but treat the geometric quantities like expansion classically. And if you like, we can include fluctuations of the metric in the stress-energy tensor. So this would require finding some regime that's bigger than the Planck scale, but not so big that the quantum fluctuations of the stress-energy tensor are unimportant. So if you look at the Ray-Choudhury equation, in that regime, expansion focuses light rays, shear focuses light rays, vorticity defocuses, but if the vorticity starts at 0, then at this approximation it remains 0. And so the crucial question is what happens with the stress-energy tensor. This is something that Fuster, Ford, and Roman have been investigating in a lot of detail lately. The answer qualitatively is that a large majority of the fluctuations in the stress-energy tensor are negative, but that there is a lower bound to the negative fluctuations, which depends on the smearing scale that you use to define these operators. But given a scale, there's a strict lower bound. Positive fluctuations are less common, but there's an infinite positive tail. So what you expect is that these frequent negative fluctuations tend to defocus light, once in a while, there will be a large positive fluctuation that focuses sharply. And then, once the expansion becomes negative and large enough, the nonlinearities take over, and no subsequent negative fluctuation can make the right-hand side of the Raychaudhuri equation positive again because there's a lower bound. So this is a phenomenon that's known in probability theory as gambler's ruin. It's the statement that if you bet against a house with infinite resources, that no matter how good the odds are in your favor, eventually you lose everything. So you can make a back-of-the-envelope estimate of this. Just take the lower bound, call that minus t, take a smearing time of delta t, and look at the probability of a positive fluctuation that is large enough, that is twice the absolute value of the lower bound, so that the left-hand side here becomes less than minus 2 times the biggest fluctuation that can take you positive. And if you assume that these fluctuations are independent, which they're not quite, but the correlations drop off, the time correlations drop off very quickly, you can do a back-of-the-envelope estimate. You find that the time it takes for the expansion to be driven to minus infinity is described by an exponential distribution with a mean value of 15 times the smearing time, which I'll take to be the Planck time. So Ricardo Mosna, João Pitelli, and I did a simulation of this in two-dimensional dilaton gravity, where we have the advantage that Fuster, Ford, and Roman have given us the exact probability distribution of fluctuations. And what we find is a time for the expansion to go back down to 0 that fits that back-of-the-envelope curve uncomfortably well. But we didn't cheat. That's really how it comes out. For the full 3+1 dimensional version, we don't have the exact probability distribution, but we have good control over the positive tail and the negative part of the distribution. So work on that is in progress, but the back-of-the-envelope estimate is roughly the same, maybe an order of magnitude longer. Okay, this is the amount of time in Planck times that it takes for an initial expansion of 0 to drop to minus infinity under the stochastic process, and this is just a frequency. So the main conclusion is that it is really true that in an average of about 15 Planck times, most of the expansion goes down to minus infinity. Here are some typical runs just to show you that this is, in fact, the behavior. You start out at expansion 0, your negative fluctuations push you up to some maximum value. You sit around there, fluctuate for a little. You get one of these rare positive fluctuations, and then you die. Okay, so what does this mean? This is not quite enough to prove that you have asymptotic silence at short distances, because there you need a larger scale picture of the behavior of light cones, and this is also a stochastic process, so there will always be some places where this doesn't happen. But it is at least an indication that quantum fluctuations at short distances give you the kind of strong focusing which is the first symptom of asymptotic silence. So where do we go? What does this mean? It means that we have a very tentative physical picture of what's going on with this dimensional reduction, which is that at short distances you have short distance asymptotic silence that leads to BKL behavior, which means that you have local Kasner spaces that pick out random and randomly bouncing preferred directions in space. This, of course, is not Lorentz invariant, but it's what people call non-systematic violation of Lorentz invariance, which turns out to be extraordinarily difficult to look for experimentally because the violation washes out because of the random variation in the direction of the violation. Can we use this? Well, there's again some old work by a number of people who, in an entirely different context, have looked at what happens with general relativity if you can split the metric into two pairs of dimensions that have different characteristic scales, which is exactly what's going on here. And you can do a lot. You can essentially write the action as an action for a two-dimensional conformal field theory. We know a lot about how to handle two-dimensional conformal field theories. And then there's also an old suggestion, again, the first mention I found of this was due to Haber, that if this happens, it also can provide a natural regulator for quantum field theory from quantum gravitational behavior. So there are a lot of things to think about. It is not obvious what the next calculation is, but maybe one of you can tell me. So thank you.
Thanks, Steve, for this nice talk. What's the infrared behavior as you go from the ultraviolet, from asymptotic silence, to infrared, where these points somehow should reassemble? What's the infrared noise? Is there an indication of that somehow these points could reassemble? And well, what would the calculation that would indicate that?
Yeah. I don't have a good general answer to that. It would be interesting to try to understand what it means to average over BKL behavior. And I have thought a little bit about that, but I'm not sure how to do that yet. CDT gives one answer, at least. I'm not sure that this is the type of dimensional reduction that takes place in CDT. We have to test that. But right, so my worry is that the quantum phenomena get completely washed out. That because in BKL behavior, if this is BKL at 15 times the Planck length, then in times on the order of 15 times the Planck time, the axes of the Kasner space bounce around randomly. You have a probability distribution which is known, but I don't know how to extract infrared results from that, except that it looks as if the average doesn't see this behavior at all.
Well, thank you for this very, provocative and inspiring talk across the board of quantum gravity. I have a questions about your last two pictures. So, have you thought about putting the two of them together? That is, asymptotic silence is some kind of classical picture dynamics, but then the gambler death or ruin as that Planck scale, as you described it very vividly, is kind of, semi-quantum. So right. Is it a next computation to kind of put the two pictures together, or you already have some way to put this classical and semi-classical picture together?
My assumption which is something that, for which there's evidence from CDT, is that this effective dimensional reduction takes place at a couple of orders of magnitude larger than the Planck scale. If that's the case, then, so what I've done here is semi-classical. It's treating the quantum fluctuations of matter, but treating the metric as classical. And at that level, the classical analysis of asymptotic silence should be fine because the metric is being treated as classical. This doesn't say what happens when you go down from this scale closer to the Planck scale. Certainly this particular argument that led to this result breaks down completely because you have products of operators. You have a square of the expansion, for instance, and the answer depends on how you regularize that and things of that sort. There are cases known where quantum expansion, the square of the expansion in the quantum Ray-Choudhury equation actually can become negative and cause divergence rather than convergence. So my hope is that this might give you a scale at which you can look for new sort of classical approximations to GR, which you can then use to take the next step down towards the Planck scale. Right. Yeah. Right. So this is, as I said, this is not yet a proof of asymptotic silence, but the characteristic feature of asymptotic silence is that the curvature is strong enough to strongly focus light rays in every direction. Now here, what you're seeing is that if you take a thin pencil of light rays in an arbitrary direction, that the cross-sectional area goes to 0. That's what the expansion going to minus infinity implies. I mean, that's really just saying that there are caustics, but there are a lot of caustics no matter what direction you look. That's symptomatic of asymptotic silence, but it's not yet equivalent.
I have a silly question about the way the dimensions add up. So asymptotic silence and light cones turning to time-like lines sound 0 + 1 dimensional, right. And you're promoting 1 + 1.
Right.
What's going on?
So there is an intermediate stage here. If you look in the cosmological models, for instance, at the singularity, if you like, to the extent that that makes sense, you really have 0 + 1 dimensional. A little bit away from that, the effect of the light cones shrinking is that neighboring points decouple. And then the effect of that is that if you just look at the classical GR field equations, you get Kasner-like behavior within each small decoupled region. So it's a question of scales again.
Okay, so let's thank the speaker again.